So I'm Heather Riley. I'm a statistician at York Health Economics Consortium, and the application that I'm going to present today was developed with my colleague Maisie, who unfortunately isn't on the call, but I just wanted to make sure she gets credit for the work she put into it. There's also previous colleagues who were involved in earlier versions of this. I think Tom and Sarah might be on the call, so it'd be interesting for them to see how this project has evolved. So I'm going to present a practical example of integrating a Python-based transmission model into an R-HTA cost effectiveness platform using the Reticulate package. Oh, I've lost my slides again. Can everyone still see them?
You can see an overview. There's no text on it, but it says overview.
Oh, good. I think it's when I try to move my face, the screen goes. Okay. Yeah, so just to give a bit of structure to the talk. I'll start with a little bit of background on the work. Then for the main part of the talk, I'll split it into two sections. So first I'll go over the transmission model itself and then the R-HTA integration. So how we link the Python model into the app using Reticulate, and also what that workflow looks like from the user perspective within that app. And then I'll finish with some discussion around some of the practical challenges we encountered and the next steps for the platform. So I'll just start with a brief bit of background. So the reason that we built a transmission model was to evaluate a household level intervention, so post-exposure prophylaxis or PEP for COVID-19. And PEP would be offered to people living with someone who's just become infected. So the intervention is targeted at the household rather than the general population. And the first box here just shows why the household matters. So once there's an index case, COVID can spread quickly amongst people living together. And that makes household members a clearly defined group for post-exposure prophylaxis. So rather than treating a broad population, the intervention is targeted at people with a known recent exposure. And the potential effect is then epidemiological. So if prophylaxis reduces infection amongst exposed contacts, it may change the number and timing of infections within the household. And then that's where the economic model comes in. So changes in infections and disease progression can affect treatment use, healthcare costs, health outcomes, and ultimately QALYs. So the model needs to capture the whole pathway, so the household exposure, transmission, the intervention effects, and then the downstream economic consequences. So for context, we had already developed the household transmission and PEP model in Python, and the economic model was initially built within Excel. And we linked the two by basically packaging the Python model as an executable, and then a VBA button in Excel would take the user input, run the executable, and return the results back to the workbook, which did work technically, but client IT environments often restrict executable files, so sharing the model was dependent on using virtual machines, and it needed additional technical support. So the issue we had wasn't really that the model couldn't run, it was difficult to distribute and maintain it. So we were looking for an alternative interface to Excel. One option would have been to build the whole user interface platform in Python using something like Dash, but we've got a really strong R coding base within the team at YHEC, particularly for HTA and cost effectiveness modeling. So yeah, rather than rewrite the transmission model in R or rebuild the whole platform in Python, we kept the existing Python transmission engine and decided to embed it within an R-HTA cost effectiveness platform. And Reticulate is that bridge between the two. So it lets Shiny pass scenario inputs to Python, receive the model outputs back into R, and then those outputs can be used directly in the cost effectiveness model. Okay, so yeah, that's why we chose a hybrid Python and R-HTA approach. And now I'll just give an overview of the transmission model. So to start with, the model represents transmission across 5 hierarchical population layers. At the base, we've got the individual level, which captures disease progression. Then we build up to within household transmission, followed by transmission between households. And then on top of that, we model interactions within cities and then between cities. So the structure lets us capture both very local transmission, like within a household, as well as broader spread across regions. And at the individual level, the disease progression is represented using 6 core infection states. So individuals start as susceptible, and these are people who are at risk of infection. They then move to the exposed class once they've had contact with an infectious individual. And these are people who are in a latent period, so they are infected, they're just not yet infectious. And after some period of time, they'll move on to one of two infectious compartments, so either symptomatic or asymptomatic. And people in these compartments are infected and infectious, so they can contribute to onward transmission. Then after infection, individuals either recover where they've got some temporary immunity or they move to the dead state. And you can see that all states in the model are at risk of death, with COVID-related mortality applied only to the symptomatic infected compartment. So the infectious disease model is made up of individual household units, and within the household, we stratify by age groups. So we have children, adults, and the elderly. And within each of those age groups, we track the 6 compartments for both treated and untreated individuals. And it's at this household level that we implement PEP within the model. So when an infection enters the household, we move everyone else from the untreated compartments across to the corresponding treated compartments. And while they're there, they experience the benefits of PEP, which I've got on a later slide. So that was the structure of an individual household, but the model is made up of a population of households. And we model both transmission within households, where individuals have the most frequent and close contact, and also transmission between households. This layer is important because households, like I said, are a key driver of transmission, especially in the early stages of a pandemic. But on top of that, we model the transmission at the city level. So households are grouped into synthetic cities, and we capture both within city and between city transmission. So in the model, prophylaxis is incorporated through its effect both on infection risk and disease progression. So firstly, it reduces the likelihood that a susceptible individual becomes infected following contact with an infected individual. For those people on PEP who do become infected, it reduces the probability of progressing to more severe symptomatic infection, and it also reduces the transmissibility of those breakthrough cases. And it also increases the recovery rates for those who do become infected. This slide's just showing a sort of model overview. So the population structure feeds into the Python SEIR transmission model, which simulates infections and disease progression over time. And the model returns daily state occupancy for the intervention and comparator arms alongside event data, so things like treatment courses, deaths, and household infections. And then those outputs are passed into the R-based cost effectiveness model. And the cost effectiveness model then translates those into clinical outcomes, including hospitalizations, ICU admissions, and then, combines these with costs and utilities. And the final outputs are the total and incremental costs and qualities and measures such as the ISA and net monetary benefit. Yes, so that was kind of a top level overview just of what the models do, and just to give an idea for the level of complexity in it. So in this part, I'll show the R-HTA application structure. So this diagram here is showing the app at 2 levels. The technical infrastructure at the top and the user-facing workflow across the middle. So starting at the top left, the application first reads in default parameters from external Excel workbooks. So this includes things like the inputs for the SAR model alongside costs and utilities and things like that. Then at the top right, the global script is the application startup script. So it's there that we load the R packages, read the external inputs, configures the Python environment, and sources all of the different Shiny modules. Then the central panel shows the main technical connection. So R-HTA provides the user interface. It manages the reactive workflow, presents results, and runs the cost effectiveness calculations. And the transmission model itself remains in Python, and then Reticulate, like I said, is the bridge between them. It allows R to call the Python model directly and receive the outputs back into R. So the main middle row here just shows how the user works with the app. So users can explore the model background, they can specify and run an SEIR scenario, review the transmission outputs, and then move into the cost effectiveness model. I'll show some screenshots of those pages later, so I won't go through each of those modules in detail here. I'm just going to focus on the middle top panel for the next few slides, so basically how that connection between Shiny and Python works. So the first practical issue is making sure that the app uses the correct Python environment wherever it's running. So at the top here, we load reticulate, and then the code checks whether we're running locally on Windows or in a hosted environment like Shiny apps. For the local development, we explicitly point R to the Python installation used by the development team. And setting required true there just means that the application fails early if that interpreter isn't available. For deployment, we use a virtual environment called seir-env, and the app essentially checks whether it already exists. And if it doesn't exist, it creates it, and then it tells Reticulate to use that environment. So the important point is that the deployed app has its own isolated Python environment, and that just makes the R to Python connection more reproducible, and it avoids depending on whatever Python packages are installed on the server. So yeah, once that environment's been selected, the next step is to make the Python SEIR model itself available to the Shiny application. So the Python code sits within the application folder rather than being installed separately as a Python package. Yes, so here we first define the location of that folder. We then import Python system module and add that folder to Python's import path. So this basically tells Python where to look for our model code when the Shiny app starts. We then import the SEIR module once globally and then store it in the R objects called SEIR. And then from that point, the Shiny server can call functions from the Python model through that object. So it's a little like importing an R package, except that the functions being called are written in Python. And then finally, we use convert equals to true there, so that the standard Python output, so things like lists, arrays, and tables, are converted into R-friendly objects for the rest of the Shiny application. So once the Python module has been imported, the next step is to run a scenario. So when the user clicks Run SEIR model, Shiny takes the selected settings and creates a named R list called pars and parameters. This is a fixed snapshot of the scenario at the point that it's run. So it includes things like simulation settings, so things like the number of households, city and mixing assumptions, and different transmission parameters. And the final two lines you can see here, they select the model function and call it with that scenario object, and then Python runs that runs the SAR simulation and returns a result object, which is just temporarily stored in res. And then the next step is to take the key returned output, so things like the state occupancy for the intervention and comparator arms, and make them available reactively to the cost effectiveness model. So the SEIR model has now run and its outputs are back in R. And the first part of this code takes the return state occupancy outputs for the intervention and comparator arms, converts them into R tables, and then stores them as reactive objects. And making the objects reactive just means that when a new SEIR scenario is run, the values update automatically. And the lower part of the code creates the CEM calculation module. So alongside the economic inputs and the trigger to run the cost effectiveness model, we also pass the SEIR calculation module through the SEIR results output. And it's at this point that we've created that connection, so the cost effectiveness module can now access the latest completed SEIR outputs. And the next slide shows what happens inside that CEM module once it receives that connection. So inside the CEM module, the first line here makes sure that an SEI run is actually being completed before any economic calculations can begin. And the next two lines retrieve the intervention and comparator state occupancy trajectories from the reactive SEIR object. And those trajectories are then passed into the proportion calculation function. And this translates the epidemiological state occupancy into the quantities needed for the economic model. Yeah, so that's a little bit of the technical workflow behind the app, and I'll just show quickly now what that process looks like from the user perspective. Sorry if this is a little bit blurry. I went with screenshots over trying to show the app live. So this is the SEIR inputs page in the app, and here the user can set up the scenario that they want to evaluate before running the transmission model. So that includes choices around number of households, dates to simulate, the different sort of disease and treatment assumptions, just depending on whatever scenario you want to look at. And once those inputs have been set, the user clicks Run Model at the top of the page, and Shiny then captures those settings as a single scenario object, sends them to the Python model, and waits for the simulation outputs to be returned. And you can see the workflow banner at the top also helps guide the user through the sequence. And once the app is run, this pop-up just confirms that the SEIR model has finished successfully, and it lets the user either go straight to the SEIR results to inspect the epidemiological outputs or continue to the cost effectiveness model. And this is the SEIR results area. I won't dwell on the numbers here because they're completely made up just to be illustrative, but it just kind of shows the types of outputs available to the user. So we've got some headline summary measures, time series plots such as daily infections by arm, and also things like visualizations of how infection spreads across the synthetic city structure. So yeah, once you've run the SEIR model, you can now move to the cost effectiveness inputs page, and the workflow banner at the top here shows that step one, running the SEIR model is complete. So you can probably just about see there's a little green tick there. And that just then guides the user to the next stage, which is to run the economic model. So here the user can then set the cost effectiveness assumptions such as perspective, costs, utilities, and clinical parameters, then click Run Calculations to generate the economic results. And then finally, this is the CEM results page. And again, the values here are just illustrative, but the page just brings together the economic outputs in tables and charts, including costs and quality breakdowns and the resultant incremental analysis. Yes, so I'll just finish by talking a bit about the practical challenges that we encountered and the main areas for future development. So first, the biggest one was the runtime being an issue in the interactive application. So the household level stochastic simulation can be quite slow. And in a Shiny app, that can affect responsiveness and create a risk of session timeouts. So the next step here is to make the execution more scalable. So for example, using queues or background jobs, clearer progress feedback for users, and maybe caching results for scenarios that have already been run. Second is the stochastic uncertainty. So a single model run is only one possible epidemic realization. And obviously to fully understand the uncertainty, we need to run repeated runs across different random seeds and then summarize the range of epidemiological and economic outcomes. So for the next step, we'd like to automate replicated runs and carry those distributions through to the cost effectiveness outputs. Third is performance at scale. So once we combine repeated stochastic runs with scenario analysis or sensitivity analysis, the computational burden can increase quite quickly. And then the last one is the cross-language deployment. So the R and Python environments need to remain compatible across development and hosted deployment, and we just need confidence that inputs and outputs are being passed correctly between the two languages. Thank you. Oh, I wasn't too over time. I was worried after the start I was going to go well over. Yeah, thanks everyone for listening. If anyone's got any questions, happy to take them.
Thank you very much, Heather. You're bang on. If anybody had any questions that they want to say out loud, they can raise their hand, but otherwise I will read some of the ones that are in the chat. So Rob starts with, he does also have a question, but he starts with a comment that, you know, we when organizing this, get the question, why focus on R? And that it's nice to see that due to the transferability of coding skills and tools like Reticulate, where you can kind of swap between the two, that doesn't actually really matter so much. And that R and Python can work together.
Yeah, definitely.
You mentioned there that the model could be a little on the slow side in parts. In relation to this, Darren had a question. Given all the layers of translation and conversion, there is, I imagine, or Darren imagines, that there is a considerable computational overhead associated. What are the runtimes like, and had you considered sort of the cost benefit of performing a conversion to R or C++? Or C++, I guess.
Yeah, so this model's gone through quite a few changes. The original model was much simpler, but we've added a lot more functionality, and runtime is a massive issue. So when I run this for 5,000 households, it takes about 1 to 2 minutes to run, which isn't too bad. The problem we've got is we've now introduced lots and lots of subgroups, so we need substantially more than 5,000 households, and we need a lot of replicates. So it sort of moves into hours at that point, which isn't ideal. What we've been doing at this point, we've run a lot of simulations on our high performance computing system at York, and we've found a balance between the stability of like the number of households we need, but also the runtime. But yeah, I do think going forward it would be good to look into some other options, and also just to speed up the code, because I'm a mathematician first, I'm a coder second. I'm by no means perfect, so there's definitely places where I'll be able to speed this up.
Thank you. Simon also had a helpful link to that there is a Shiny for Python. Rob, if your hand there.
Yeah, just a comment on that. I think regardless of how good a programmer you are, I think you probably got to the point if you're wanting to run probabilistic models on a SAR simulation, you're going to basically be forced to run these asynchronously. So trigger an API call, have it run on a remote server, and then come back a day later and look at the results in the app rather than actually running them in the app. I don't think it's a case of being a good or bad programmer at that point.
Yeah,
Yeah, I think it's just such a big model to run that it's going to take a long time. So yeah.
thank you for that.
Rob, while you're there, you also had a question about vaccines.
So focus on the sort of decision problem and the model itself. During the pandemic, we had the problem that we had rapidly emergent variants, and I didn't know how whether you capture in here sort of variants and immune escape from specific vaccines, or whether COVID is treated as kind of a homogeneous single disease.
No, so we've got so many different models. The model that we're looking at here, the client wanted to look at a scenario where no one's vaccinated. It's just a completely new variant has emerged. It's highly transmissible. So it's all very theoretical in this version of the model.
Thank you very much for that. Thank you, everyone.